someone I pressed F4. Morning is at F4. Now if I put F5, it will come back from here. Or then, from here. Oh, I am correct. Thank you. Then next is, we have gone through AND, OR, NOT functions. So, NAND, NOR function, exclusive OR function. In the compact form, it is called XOR function. XOR function is a very key and important function in Boolean algebra as well as here in a number realizations. It's a very important function. Just okay, as we use it, we can just get a feel of the potential. The symbol for that is this: A XOR B. This is the symbol used. Okay, it's one of the special symbols available in the PC word. Y equals A XOR B. Now here, this is what it says. Output is true only if the two inputs are unlike each other. Basically, an XOR function is a function of just only two logic variables. AND function, OR function, I can use 3, 4, any number of variables. Here it's only two logic variables. If both are 1, output is 0. If both are 0, output is 1. If the two are unlike each other, then the flag is up. Okay? That is, there should be a definite disagreement between the two inputs. Then only the output is high. Okay? That is the XOR function. It is a unique function. So that's a symbol. This is a symbol and this is a truth table. You can see here, output becomes 1 only if these two are unlike each other. 0 and 1, 1. Or 1 and 0, 1. Only if the two inputs are unlike each other, output is high. There are a number of laws and theorems which go with Boolean algebra. They essentially help us simplify functions or establishing identities. You can easily realize this function is same as that and so on. As far as proof is concerned, I will not worry about the proof. We'll just go ahead at the statements. Wherever you are particular about proof, you just put the truth table and check up and confirm that that is satisfied. That's all what is required. No big proof is required. If the truth table is satisfied, that is proved. Somebody else comes in. No. See, these are typical laws. This says that A or B is same as B or A. A and B is same as B and A. A or B, however you reverse, it is same. It is obvious for us. Similarly, A and B is equal to B and A. This is associative law. Whatever you do with three of them, whether you do first with the first two or the other way around, it is the same. Again for AND and OR functions. This is called the distributive law. Okay? It says that this is same as this. It is as good as removing the brackets. In conventional algebra, it is as good as removing the brackets. This circuit is same as this. That is, first I do an OR operation and then AND operation, or I can do the other way around. That is, I can AND A with B, and A with C, and then do an OR operation. Or I can do the other way around. Okay? There's an equivalence between the two. Just see here, you can easily realize there's an here this is obvious. The statement is obvious. If you look at the circuit, it is not so obvious, but the two are identical. So if you want to realize this function, you can do this with less electronic components. These are laws of AND and OR operations. Everything you can check up with truth table. Many of these are obvious. So okay, A with 100 with 0. Anything under 0 is 0. Anything with 100 with 1 doesn't change. You add you OR with 0 to something, it doesn't change. You OR something with 1, it is 1, and so on. A and A bar, it is 0. That is from something, its complement. The AND operation is 0. Something or its complement is always 1. When you complement a function twice, you get the original function. This is a very well-known theorem which allows us to identify, simplify a number of functions. It's called the De Morgan's theorem. You can check up, verify by truth table. It says there are two statements. These are the duals of, one is the dual of the other. It says that A or B bar is A bar, A and B bar is A bar or B bar. The reverse. Okay, I'll come here first. A and B, we have bubble here, which is essentially a NAND gate. It is equivalent to a OR gate with bubbles on this side. A bar, B bar, OR. The reverse, the dual of that. A or B with a bar. A or B with a bubble here. It is equivalent to this, an AND gate to which the inputs are A bar and B bar. It essentially says that I have an AND function with a bubble at the output side. I got an AND function with an inversion at the output side is equivalent to an OR function with inversion at the input side. That's all what it says. An AND function with inversion at the output side is equal to an OR function with inversion at the input side. The reverse. An AND function, I'm sorry, this is definitely mine. An OR function with a bubble at the output side, right, correct this, an OR function with a bubble at the output side is equivalent to an AND function with bubbles at the input side. So the other one, that is equivalent to this is equivalent to this. If I take any Boolean function, any Boolean relationship rather, it has a corresponding dual relationship. This is what it says. I take one relationship, one Boolean equation I take, every AND operation I change to an OR operation, every OR operation I change to an AND operation, complement any 1 and 0. That's an equivalent theorem. Actually, if we go back, this is what this says. See here, this is a Boolean relation. The Boolean relation. It is equivalent. From this I get this. Here, every AND operation I convert it to OR operation. Every OR operation I convert it to AND operation. I got an equivalent relationship. Okay. Same thing I repeated here. One more thing I would like to point out, and just leave it here. I may have a Boolean function which I may realize like say A or B and C or D bar and E bar or F, D plus E bar, F plus E bar, and so on. This is a Boolean function. I got all sorts of AND and OR operations working all over the place. Number of activities are here. Okay. If I directly try to realize this, I may go for a very big, let me try this. I don't know if I will succeed here. A or B. Then this I am ANDing with C. Then I am ORing with this D bar. and E bar. For this, I do an OR operation. So I have here an F. I have the same D here. T and E bar I take. So that will be T and E bar. I put an R here. Then F and C bar. I have an F or C bar. This is a function. If I put here y equal to this, then this will be y. So I got a number of inputs, A, B, C, D, E, F. I know I have not given F anywhere. I hope this is F. Okay. I got A, B, C. I got 6 input variables. I got an output variable. Here you see here I got 1, 2, 3, 4, 5 layers of circuits. But if I take a signal, if I take this signal, if I take a signal coming here, it has to go through 1 gate, 2 gates, 3, 4, 5. See here, this A, if A changes, it has to, A changes, it has to go through all this to make its presence at Y. 1 gate, 2nd gate, 3rd gate, 4th gate, 5th gate. I think all others are 5 or less. There are 5 layers of gates. There are 5 layers of gates here. Okay? Others may be less. Now, I can show that I can simplify the function. I can simplify a function, logic function, and any logic function you can express as a 2-layer function. Only 2 layers are enough. By some simplification, by just, you just do your theorems and then simplify. With 2 layers, you'll be able to realize any logic function. For example, here if I try to simplify this, I'll get here. This will give me AC plus RAD bar or no. AC or BC or D bar multiplied by, R and E bar or F DF or FDC bar, FDC bar or F E bar F or F E bar C bar equal to Y. That is equal to AC E bar, BC E bar, D bar E bar, F D F, F D C bar, F E bar F, F E bar C bar. So, to realize this function, I realize this AND function, and OR. So I will have a number of AND functions. I take all of them and do an OR operation. That will give me the output. One level, second level. So any Boolean function, you can show that you can simplify to this level. Apparently it will appear to be quite complex, but with a two-layer representation, you can realize any Boolean function. It is a very important result that we use in all circuits. You can simplify, optimize circuits and so on. The applications of logic circuits are wide and varied. We will just take only 3 examples which are very commonly used and we also may require for our further classes. There are 3 categories. One is a multiplexer and a demultiplexer, data encoder, decoder, and typical algebraic circuits. We will take a few of these representative ones and discuss in some detail. Again, continue. This is called a 2-to-1 multiplexer. It's more often called a 2-to-1 mux. 2-to-1. If you say 2-to-1 multiplexer, you will say that is in the first class of digital electronics. After the first class of digital electronics, if you say 2-to-1 mux, it means you know digital electronics. So mux, demux. Now, coming to the operation, it is very simple. See, if I take this S signal, that's a select signal. It's a control signal. If S is 1, S bar is 0. It's okay? S is 1, S bar is, if S bar is 0, this AND gate output will be always 0. It's alright? S bar is 0, this G2 AND gate output is 0. So the G2 AND gate will not come into picture at all. This is an OR gate, see here. This is an OR gate here, this is 0. So that OR gate will not bother about this input at all. It's alright? That is cut off. Now S is 1. If S is 1, I1 will decide this output. S is 1, this is an AND gate. If I1 is 1, output will be 1. If I1 is 0, output will be 0. It's okay? This is an OR gate. This is anyway 0. If this is 0, output is 0. If this is 1, output is 1. What I mean is, as long as S is 1, this I1 is directly steered to the output sign. Am I clear? Is alright? It's okay? That is a mux. Mux is a multiplexer. This fellow is 1. It simply takes this signal and makes it available here. It simply cuts off this signal. It's okay? It's alright? You take the reverse case. S is 0. The select signal has a value 0. If the select signal has a value 0, this is selected. This is cut off. This is 0, so this is cut off. This is always 0. This is the output side. So by just controlling the select signal, by making it 0 or 1, I can just allow this signal to come here or this signal to come here. You are multiplexing the 2 inputs. I can take input from one or take input from the other and make it available in the output side. This is called a 2-to-1 match. From 2 signals, 2 input signals, I generated 1 output signal. It's a 2-to-1 match. It's okay? I have shown typical operation waveform. See here, initially S is high, S is 1, hereafter S is 0. The second typical operation. This I1 is a square wave which changes very fast. This changes at half the rate. Up to this time, output follows I1. Thereafter, it follows I2. It's okay? I don't know what some mistake I made here. Circuit will not do this. Just I extended the concept. This is a 4-to-1 match. This is a 4-to-1 match. There are 2 control signals, S1 and S2. With the two control signals, you can select any one of these four, I1, I0, I1, I2, I3, any one of them you can select and make it available as the output. That is, if I want to make this I0 available at the output, this is an OR gate. It's an OR gate, this is a short representation of that OR gate. If I want this to be made available at the output side, I have to do two things. Number one, I have to make every one of them 0. All these three 0. I have to make these two 1. Is it alright? This is a 3 input AND gate. These two are the select signals. If I make these two 1, this output will be reset by only this. Is it okay? One thing I have to do, both of them I have to make 1. Then this output will be, this input will be just that output. That's one thing I have to do. Simultaneously, I have to make every one of these 0. Then this output will be, this input will be made available at the output side. If I make S0, S0, S1, both as 0, 0, you please check whether that is satisfied. S0 and S1 both 0, 0. This is 0, this is 0. This is 1, this is 1. Both these are coming here. Both these are 1, 1. It's okay? As far as these gates are concerned, at least one of the other inputs is 0. So they are all deselected. Only this fellow is selected. It's okay? If I go a bit further, if I go one step further, I have got select signals S1, S0. If I make both of them 0, 0, I1 goes to output. I'm sorry, I0 goes to output. 0, 1, I1 goes to output. 1, 0, I2 goes to output. 1, 1, I3 goes to output. Is all right? I interpret it as a binary number. If the binary number value is 0, 0 signal is going. If the binary number value is 3, signal 3 is going. Is all right? I can use one select signal, I can multiplex 2 signals. I use 2 select signals, I can multiplex 4 input signals into 1. If I use 3 select signals, I can multiplex 8 to 1. And so on I can continue. You just to see, we have started with Boolean algebra, yes, no, basic AND relation, OR relation. You are given interpretation. I prepared a circuit, I worked out the logic, I given a complete design for multiplexing signals. How do you select one signal out of 8? This is what you do. How do you select the second signal out of 8? This is what you do. You just build up like this. It's okay? This is the reverse process. DMX. One signal line, I want to steer to one output side or the other output side. 1 to 2 DMX it is called. Demultiplexing from one input line into one or the other. You can see here, input line if I take, if S is 1, this is 1. If S is 1, this is 0. So this output will be always 0. It will not change. If S is 1, S bar is 0, this output will never change. It will remain always at 0. But this fellow will change whenever this I is changing. You can see here, that is input. As long as S is 0, output 0, I'm sorry, this will be output 1 and 2, am I right? 1 and, so 1 is reflected on this. When S goes to 1, it goes to the other one. One signal, you steer to one path or the second path. If S is 0, you steer to first path. If S is 1, you steer to the second path. I build up on this. Same thing I'll build up. I don't know, I have put here. See here, 1 to 4 DMAX. I taken a signal, I'm steering into circuit number 0, circuit number 1, circuit number 2, circuit number 3. I got alternatives, 4 alternatives. I can choose any one of them and make the input available on the first one, second one and so on with 2 control signals. I can build up, I can put 3 control signals. I can select from any one of the 8. Is all right? Procedure is same. So we have briefly discussed how to multiplex signals, how to demultiplex signals. When I say signal, a digital line which will carry a 0 or a 1. For some time I will connect to this, then I will connect to the other one, and so on. Then circuits for algebra. I can continue? Oh, I will not bother. Guru Ayappan is saying that you have worked with that, there is some more problem than what I am talking about. I will talk of only the rosy things. Okay. Now, normally, if you work with the microcontroller proper, this may not matter. Only when you do the interfacing, it may matter. I think we will discuss that separately. Okay. I have taken the case of adding just 2 binary bits. 2 binary bits. A and B are 2 bits. I want to sum up the bits. A plus B. When I say A plus B, here I am talking of algebra. In the other case, this plus is not, it is an OR signal. Okay, always, that Dr. Subramaniam used to be very fussy. If I call this as, in Boolean algebra, if I call it as plus, his blood pressure will go up. He says, he'll give compliments. In numerical algebra, this is a plus signal. A plus B. There it is an OR signal. There are 2 separate words. Okay. Now if I take 0 and 0, I'll get a 0. If I take 0, 1, I'll get a 1. 1, 0, I'll get a 1. 1, 1, I'll get a 1, 0. This is a sum bit. This is a carry bit. When I sum up 2 bits, I'll get a sum bit and a carry bit. In some cases, the sum bit is 1, the carry bit is 0, on the other way around, carry bit is 1 or sum bit is 0. Now you please check up, put the truth table for summing, check whether this truth table is okay, whether that conforms to that. Is it all right? The sum operation is an exclusive operation. The sum operation is an exclusive operation. That is, if the 2 bits are unlike each other, sum is 1. It's okay? The 2 bits are unlike each other, the sum is 1. The carry is an AND operation. If first bit is 1, second bit is 1, then only there is a carry bit. It's okay? The first bit has to be 1, second bit has to be 1, then only there is a carry bit. So if I want to add 2 binary bits, single bit numbers, if I want to add 2 binary single bit numbers, I require 2 gates. One is an exclusive OR gate, the other is an AND gate. If I use an exclusive OR gate and an AND gate together, I have created an adder circuit, a basic adder circuit. 2 bits I want to add, I got a basic adder circuit. It's okay? I'll come back here. That's all. To add 2 bits, I put an exclusive circuit to get a sum. I put an AND to get a carry. Okay? This is called a half adder. In digital terminology, it's called a half adder. It's okay? If you understand this, basic circuit, you know everything about realizing the complete algebra and the corresponding circuit. Just you have to understand this, that's all. You repeat in various ways, crisscross. You can put multi-bit adders, you can put multiplier, etc. Whatever circuit, subtraction, anything you want, you can just go on putting it all over the place. Just to put, not at random, put in some orderly fashion, you will get an algebraic operation. Now I am going one step further. Earlier, what I discussed earlier was just adding two binary bits, adding one bit with another bit. It is like adding two decimal digits, nothing more. But suppose I got an adder which I have to add multi-bit numbers. I got one number like this, 1 1 0 1 1 1 1 0 1 1 1 0 0 1. I got two numbers like this. I want to make an adder. If I want to make an adder for this, the basic unit I should do is something somewhere in the middle. It should do an addition. So this number I call A. This number I call B. So it should be able to take this AI and BI and do an addition. When I take an AI and BI, see here, it has accepted a possible carry bit from the previous stage. When I do the previous addition, I may get a carry bit, a 0 or a 1, I don't know. Depending on the numbers, it can be 0, it can be 1. I can get a carry bit. So it should accept AI, BI plus a carry bit input. And it should generate a sum bit and a carry bit to the next stage. Is all right? So in a binary adder chain, somewhere in the middle, if I consider addition of two bits, it should accept three inputs, the two bits plus a possible carry from the previous stage, and it should generate two outputs, a sum bit and a carry to the stage that follows. That is called a full adder. It's called a full adder because it does whatever is expected of the addition in the chain. The other thing is just only half the job. It's called a half adder. It's a full adder. Now for a full adder, I give the logic here. You can see here. You take a half adder, AI, BI you take, generate the sum, take the carry. For the previous stage, take that carry, take this sum, and you will get the sum bit. That's okay? That's alright? So one half adder, another half adder. The two together will generate the sum bit. You will get a carry bit here. From these two you have to generate the carry bit. You put just an OR gate, that's enough. Both of them won't be 1. Either this will be a 1 or this will be a 1. That you can make out easily. Only one of them will be 1. So you need to put only an OR gate. So two half adders and an OR gate together make up a full adder. Ci minus 1. Now what I was saying? This is a 7-bit binary number. This is another 7-bit binary number. I want to add the two. I put number of adders and put. There I take one stage. If I take this stage, this has to accept these two and add. Plus when I add these two, I may get a carry. When I add these two, I may get a carry, I should add here. From here I will get a carry, I should add here. So that Ci is a carry from the previous stage. I don't know if I am clear. So if you put, what I am saying for the first stage, you put only a half adder. In multi-bit, what Arul is saying is, Arul is giving a theorem. If you want to make multi-bit adders, the first stage you need to put only a half adder. You take the trouble of full adders for further stages. Correct? Is it alright? It's okay. It's okay. See here, a nibble, actually a 4-bit number is a nibble. a 4-bit number is called a nibble. I have shown the circuit to add two 4-bit numbers. My service said I put only a half adder here, generate that carry, full adder, carry, full adder, carry, full adder, carry. These 4 are the 4 sum bits. This is the carry bit. Alright? That's a nibble adder. Now if I put a full adder here, you can accept a carry input. You can use it to add nibbles. In the big binary chain, you can add nibbles like this. Suppose you are having only a full adder, you simply make it 0. Okay. I think I'll take a few minutes off, I'll come. F5 Sumar. F4. Escape. Just I'll take some water. A few minutes you give me. Nothing more is required to be known. Rest only logic. You should know how to. Okay, for addition this is what I do. Subtraction this is what I have to do. Multiplication this is what I have to do. What we went through in the morning for algebra with binary numbers. If you understood that, you can have a one-to-one relationship with corresponding circuits, with half adders, XOR gates, etc. You can build up any algebra activity that you want. Just example is the nibble adder that we discussed earlier. Here I have shown a half subtractor. You see whether that is okay. You make the truth table for subtraction and just see this is the half subtractor. Is it alright? The half subtractor, what it does is, A minus B, A, B. If A and B are 0, 0, the, what do you call that? D, difference. If A and B are 0, 0, difference is 0. If A and B are 1, 1, difference is 0. Is alright? If A is 1, okay, let me continue with that borrow also. Here I don't borrow from the previous stage, borrow is 0. I don't borrow here. If A is 1, B is 0, difference is 1, I don't borrow. Is alright? A is larger than B, difference is 1, I do no borrowing. If A is 0, B is 1, I borrow a bit from the previous stage, that becomes 1, 0, minus 1, difference is 1, borrow bit is 1. So if I want to subtract 1 bit from the other, I should generate a borrow bit. I want to borrow from the stage on the left side. I want to generate a difference bit. 2 bits I have to generate, 2 functions. See here this function. Difference function is just an XOR function. Is it alright? This difference function, it is 1 only if the 2 are unlike each other. A and B are unlike each other, so the difference function is 1. That is generated by an XOR function. This represents an XOR function. That generates a difference bit. For the other one, I should take this, take an AND and put it here. Is it alright? Is it okay? That is a half subtractor. That is, I can use only for this last fellow. You can make a full subtractor, you can make a nibble subtractor, 8-bit subtractor, you can just go on building up. Okay, I have not done any of those here. I have not done any of those here. What I have shown here is doing subtraction by adding 2's complement. A and B are 2 numbers. I want to subtract B from A. Subtract B from A. For that what you do is, Number 1, get 1's complement of B. Okay? You have to get 1's complement of B, add 1. One's complement of means complement every bit of B. It's alright? I complement every bit of B, that is 1's complement. Then add 1. That gives me 2's complement of B. Okay? Add to A. Add to A, then what? To hell with carry. Just ignore the carry. Okay? Assuming it's a positive number. If it's a negative number, take that carry and do whatever you want. This is what I am doing here. Just see here. Is it okay? Yeah, I taken every bit of B. I just inverted that. I complemented every bit of B. Okay? Then I put an adder. The multi-bit adder that we discussed earlier, I just repeated here. This adder, this 4-bit adder, I just repeated here. Then I am adding a 1 here. Well, this should be a full adder now. Okay. Actually, what I did, I took that figure, I did a pasting here. I forgot to make the change. This should be a full adder. Okay, if you don't make that change, the computer will make a mistake for you. So I get the carry, I get the output bits. If the carry bit is 1, ignore, output is positive. If it is 0, output is available in 2's complement form. You just see the versatility of the whole thing. I started off from Boolean algebra, binary number, I have combined the two, I am building up the complete algebra. I think multiplication we'll do tomorrow.